Section 6.2, Radicals and Rational Exponents. This is a continuation of the exponent rules that we've learned before. What we're going to be doing is including the connection between exponents and another important notation called radicals. Now you have seen radicals before because a square root is an example of a radical. We can start with a very basic example here. This is something that you've seen before. You know that 2 squared equals 4. It means 2 times itself. 2 times 2 equals 4. And at the same time, you've seen the notation before that the square root of 4 would equal 2. That's just a connection between those two things there. But we don't have to stop at just doing 2 to the second power. We could expand that and look at 2 to the third power. And that's 2 times 2 times 2, which is 8. And we introduced this other notation, which you've probably seen before, called a cube root. We have a little 3 here next to what we call the radical. We'll get into that. But it looks like the square root symbol with this shape here, but we have a little 3. And the cubed root is what we call this, of 8 equals 2. And the reason for that is because 2 to the third equals 8. We have to ask ourselves, what times itself 3 times gives us 8? The answer is 2. Just like what times itself twice equals 4, and the answer there would be 2 as well. We could once again take this a step further and look at 2 to the fourth. Just keep on multiplying by 2 until you get 16, and that leads us to the similar fact that the fourth root of 16 would equal 2. What times itself 4 times equals 16? The answer is 2, as we've shown right here. This could go on and on. There's really no stop to this. 2 to the fifth is 32, and for similar reasons, the fifth root of 32 equals 2. Now, not all the time will all the radicals, which is what these are here, come out to being 2. I just wanted to illustrate this using some basic facts, using powers of 2 to see just how easy that is. Well, we usually work with the square root or even the cube root. We actually can find the nth root of a number for any positive whole number n. Typically, we won't talk about the first root where n equals 1 because it's not an interesting case. Usually it will be above 2 or 3 for this section, but what you will encounter mostly during your mathematical studies is a square root or a cube root. Either way, any problem asking for the nth root of a number has a setup like this. The index is this small number n that goes in front of the radical, almost on the top left. That's the number of times that the number is going to multiply by itself to give us the value inside, a, which we call the radicand. So we have the index and the radicand. Those are our 2 really important pieces that come together to form an entire expression, which is called a radical. Sometimes the radical just refers to the shape, what we used to call a square root symbol, but we know that it doesn't just mean square roots, so we want to expand it to mean more than just square roots, and so that's why we use the term radical. Now, this expression will equal a certain number, and that number is going to be found by figuring out what number times itself n times will give us the value of a. So that's why I've shown the connection to the exponential expression here. X times itself n times equals a. That's what x to the nth means. And so we can see this in practice. Looking at my first example here, I'm asking for the cube root of negative 27. Negative 27 here is my radicand. 3 is my index. So what I want to figure out is what times itself 3 times equals negative 27. Well, with some trial and error or a couple of other things, I might realize that my answer is going to be negative 3. And the reason for that is because negative 3 times negative 3 times negative 3 equals negative 27. That's the connection between the radical and the exponent. I could write it as negative 3 to the third. And my exponent here is the same as my index here. Negative times a negative times a negative ends up leaving me with another negative, the negative 27, which was my original radicand. By employing the same logic over here, I can figure out the fourth root of 16 by determining what number times itself 4 times equals 16. I might remember it from the previous page or by trial and error, but ultimately I'd get an answer of 2. And that's because 2 times 2 times 2 times 2, which is the same thing as 2 to the fourth, equals 16. And so in both of these cases, I've determined what number, 2 or negative 3, times itself the number of times indicated by the index, 4 or 3, equals the radicand, 16, negative 27. Negative 3 to the third power is negative 27. 2 to the fourth power is 16. And that's why the cubed root of negative 27 is negative 3, and the fourth root of 16 is 2. That's how you evaluate the nth root of a number. Radicals present a very interesting problem when we're dealing with negatives, and something we have to be very careful about. What I'm starting off with on the side here is just some given information to help make this page a little bit easier. It would be very easy to show that 2 to the 6th equals 64, and the same thing is true of 4 to the 3rd. 2 times itself 6 times, and 4 times itself 3 times, both equal 64. Using that information, these first two radicals are very easy to evaluate. The cubed root, or the third root of 64, is just the number times itself 3 times it equals 64. Based on my given information, that has to be 4. Similarly, the sixth root of 64 is the number times itself 6 times that equals 64, which again, for my given information, is shown to be 2. Now in these next two radicals, going down, I notice that the only difference between the first two in these is that I have a negative out front of the radical. In these situations, I first evaluate the radical and then I just make my answer negative. So in this example, negative third root of 64, I first need to figure out the third root of 64, which I've already shown to be 4, and then just make my answer negative. Same thing applies for the second one. Negative the sixth root of 64, I've already shown that the sixth root of 64 is 2, and then I just make my answer negative. Those 4 don't pose any type of an interesting problem for us. Now, when I look at these examples on the right, I notice that my radicand itself, the number inside the radical, is negative, and that's very different from all of these where the radicand was positive. In this first problem, I'm trying to figure out the third root of negative 64. What number times itself 3 times equals negative 64? Well, I know 4 times itself 3 times equals a positive 64. And if I multiply a negative number by itself 3 times, it too will end up being negative. Therefore, the third root of negative 64 is negative 4. Negative 4 times negative 4 times negative 4 is negative 64. The next example is almost identical, but there's also a negative on the outside. One thing you're going to be tempted to do is try to cancel these negatives out. Don't do it. You're not allowed to cancel out something that's outside the radical and something that's inside the radical. Don't think about it as a fraction bar that allows you to do something like that. Instead, just evaluate the radical first and then make your answer negative. In the previous example, we showed that the Third root of negative 64 was negative 4. And now I just need to make my answer negative. But since it's already negative, a negative times a negative equals a positive 4. Once I evaluate, I get rid of the radical, and now the negatives can combine to make it positive. Now I come down to this example, the sixth root of negative 64. We may be tempted to look at this fact up here and say 2 to the sixth equals 64. Therefore, the sixth root of negative 64 would equal negative 2. But the truth is that that is not the case. If you do negative 2 times itself 6 times, you'll notice that you would actually end up getting a positive 64. It's impossible to raise any number to a certain even power and end up with a negative answer. So, if the radical has an index that's even, like 6, 4, 2, or 8, and a radicand that's negative, we cannot get a real answer. And that's where we introduce imaginary numbers. If your index is even and your radicand is negative, the answer is non-real. It's imaginary. So you cannot get an answer for this yet. Eventually we will learn a way to express it, but at this point we can just say that the answer is non-real or imaginary. It is possible to express any radical expression using rational exponents. Rational exponent, also called a fractional exponent, just has two parts, a numerator and a denominator. Those two parts correspond to different parts of a radical expression. When I say a raised to the power of m over n, my numerator m becomes an exponent on a radical expression, while my denominator n becomes the index of the radical. It's also possible to raise the a to the mth power first and then determine the mth root, but we'll find for our practices that it's almost always going to be easier to determine the nth root of a first and then raise that answer to the power of m. Let's see what this looks like in practice. When I say 27 to the 2/3, what I'm interested in looking at is figuring out what number times itself a certain number of times equals 27. The way to determine that is to first rewrite this using radical form. I'm going to start by taking my base, 27, and making that my radicand. My original denominator of 3 will serve as my index. So here I'm talking about the third root or the cube root. Then my original numerator 2 will be an exponent to which I will raise that value. The third root of 27, as I've seen before, is 3. 3 to the third power is 27. 3 times 3 times 3. I'm going to take that answer and square it. And my result is 9. 27 to the 2/3 equals 9. Similar process for my other example, negative 32 to the 3/5. Establish my radical and make sure that I include the negative in my radicand since it was in parentheses to begin with. My index is 5, I'm talking about the fifth root, and I'm going to raise this to the power of 3 once I evaluate my radical. The fifth root of negative 32. Now even though my radicand is negative, because my index is odd, I know that I can do the work. And what times itself 5 times equals negative 32? Well, that's just negative 2. Then I have negative 2 to the third power. Negative 2 times negative 2 times negative 2 is a negative 8. So negative 32 to the 3/5 power equals negative 8. By rewriting my rational exponents as a radical expression, I was able to very easily evaluate each problem. Well, we have definitely gotten through the meat of the lesson. There are just a couple of special cases we want to look at. What happens if I want to write a radical expression using rational exponents, but I seem to be missing either my exponent or the index? It would seem that I would need both pieces to get the numerator and denominator, but sometimes they're not obvious to me right away. Well, whenever I have a radical without an index, the invisible index there is actually a 2, which you know because it's the square root. That's the first radical you ever saw. And when you are dealing with the square root, you know it's the number times itself 2 times that gives you the radicand. So that's how we know that we're going to be using 2 as our missing index. In this case, we could rewrite the square root of x to the third as x to the 3 over 2. 3 was originally an exponent, so it becomes my numerator. 2 is my index, it becomes my denominator. With this particular problem, since I don't have a number for x, I can't go any further. It's just how we would rewrite it. Similarly, for the fourth root of y, without an exponent visible, I actually could say that my invisible exponent is 1, so that it's possible to rewrite the fourth root of y as y to the 1 over 4. This happens a lot. Anytime you don't see the exponent, your numerator will become 1 because an invisible exponent is 1. The 4 was my index, it becomes my denominator. The thing to remember here is that an invisible index equals 2, whereas an invisible exponent equals 1. One last final example for this section. Being asked to, without a calculator, determine an approximate value for the following expression: the 10th root of 68 to the 5th power. This seems overwhelming. We're being asked to determine what number times itself 10 times equals 68, and then raise that number to the 5th power. I know I'm going to be working with decimals since it's not going to work out nicely, and without a calculator, I don't want to do that. Fortunately, using rational exponents, we have a solution. I look here at my radical expression and I see 5 as an exponent and 10 as an index. That means that I can rewrite this expression as 68 to some power, that power being a fraction. My exponent of 5 becomes my numerator, and my index of 10 becomes my denominator. Well, when I look at my exponent, it's just a fraction, 5/10, which can actually be reduced. So 68 to the 5/10 would be the same thing as 68 to the 1/2. And when I look at that there, I think I could rewrite that in a simpler radical. So when I take 68 to the 1/2 and rewrite that in radical form, the 68 is my radicand, my index is 2, and my exponent is 1, which I just discussed on the previous page were the values of the invisible index and exponent. All that I'm actually looking for is the square root of 68. What times itself twice equals 68? That's a lot easier to figure out than what we originally thought. Well, we can't do it exactly without a calculator. We do have an ability to think about what number would fit in there. I know that 8 times 8 equals 64. And I know that 9 times 9 equals 81. Therefore, the square root of 68 is going to be between 8 and 9, and it's probably going to be closer to 8 because 68 is closer to 64 than it is to 81. We can take a couple of guesses, but the bottom line is that if you're within a certain range, you'll be all set. I'm going to guess that this is about 8.2, a little bit more than 8. I could certainly use a calculator to check this, and I would encourage you to do that now. But that's just one application of rational exponents to help simplify a really complicated expression.